So if I look at this first one, the derivative of e to the something is e to the something times then our chain rule piece. So we're going to have e to the x squared plus 3 times 2x. And you could write that as 2x plus 0 if you wanted in terms of that derivative, but there's no need to. On the second one, though, we do have a product between the x and the e to the 4x. So when we go to find that derivative using product rule, derivative of x is going to be 1, and then I'll leave the e to the 4x alone, plus we leave the x alone and take the derivative of e to the 4x. I think I mentioned this on Monday, but the number one mistake that I see with something like e to the 4x is forgetting that chain rule piece, forgetting to multiply by the 4. Somehow our brain knows we should be doing chain rule if there's something complicated up there in the exponent, but if it's just a number times x, it's easier to overlook. Okay, let's dive into the dreaded logs. For me, logs are kind of in that category like fractions, where some people's brains just see logs and they're like, I'm out. Or worse, your brain's like, oh my God, logs, panic mode, and you just start throwing math at it, trying to make it go away. So really, logs and exponents are just two different versions of writing the same thing. So if I wrote something like log base 2 of 8 is equal to 3, that notation is because 2 raised to the 3rd power is equal to 8. So these are just two different ways to write the same statement. This one's our logarithmic form. This one's our exponential form. Logs can have any base at all. So if I wrote log base 10 of 100 is equal to 2, that's because 10 raised to the 2nd power is equal to 100. Notation-wise, when we have a log with a base of 10, our textbook chooses the notation that we don't have to write the 10. Now, the reason that I say our textbook is that in some other countries, in some other textbooks, a lot of time in engineering textbooks, if I write log 100, our textbook knows that the implied missing base is 10, but in some books, the implied missing base would be E. In our textbook, right, so this notation in our textbook is equivalent to saying log base 10 of 100. In our textbook, if the base is E, they're going to use the natural log or ln. So if I had, I'll start with the exponential side. If I wrote e to the x is equal to, I don't know, 7, then as a log statement, I could write this as log base e of 7 is equal to x. But the notation that our textbook would use is to write that as ln of 7 would be equal to x. Yeah.
Why does our textbook change it to times 7?
So it's not ln times 7. So that's actually, that piece of it is important. The way that we read it is meaningful. This is the log, the natural log of 7 is equal to x. That's how we would read this. Natural log of 7 is equal to x. Now, I would say that at least in the United States, this is the more common notation, but in some other countries or some other textbooks, writing log 7 would imply natural log of 7. So it is important to be careful and to check in. I don't happen to know what notation your instructor is using. I'm going to assume he's going to stick with the notation of the textbook, which is to write the natural log as the letter L and then N. Oh, do you know? I can, but it's stuff I didn't want you to write down.
Oh.
Yeah. So I started to write it and then I was like, nope, I don't want you to write that down. So I'm not even going to. Yeah. So this is the notation that our book uses. Yeah.
Is there a difference why for the log-based C or the personal log-based C or eight, like why eight is not parentheses?
Oh, nope. It can, by convention, we usually put the number in parentheses if it is bigger than a single digit. But having this in parentheses would mean exactly the same thing. Yeah. And sometimes we'll see the numbers in parentheses, sometimes we won't, sometimes we'll see a variable in there in parentheses, sometimes we won't, but those notations are interchangeable. Yeah.
Just a quick thing to clarify that when it's log base E, it goes straight to natural log, right?
Yeah, you actually won't see that notation of log base E of 7. That will never be written in the book. It'll always be written as natural log 7. The one to be careful of, and no matter where you're living or what book you're looking in, this notation always means that the base is E. Anytime we use LN. The one that can change is the LOG notation. So our textbook uses LOG to mean that the missing base was 10. And I don't know whether you got far enough in the notes on Monday for us to tell which notation your instructor is using.
She basically just.
He's using LN, sweet. That's all I needed to know. So if he's using the LN notation, then that means that if we write LOG, it will imply that the base is 10. So he's using the same notation as the textbook. That was kind of my guess. But good to know. Good to have that confirmed. Yeah. Okay. So there are a couple of times that logs are going to be important in our lives. And in general, logs are a tool that allow us to bring things down from the exponents. Now, let's talk through kind of what our basic set of log rules is, just like we talked through the additive law of exponents for exponent stuff. It's going to be important that we can play around and manipulate using some log rules. And I always kind of go back to this, and I like to keep it around log base 2 of 8 is equal to 3 because 2 to the third is equal to 8. And I just like to have that sitting around whenever I'm doing log problems. So if I get lost on what goes where, I can always fall back to that. The first of our log rules kind of goes along with the additive law of exponents. And that is that if I have log of, I'll just call this A times B, that's equivalent to log of A plus log of B. Now, the reason that that's happening is that the answer to the log question, right, like log of some stuff equals, that sort of answer part is the exponent. So it makes sense that I add the exponents when I'm multiplying two things with the same base. This is the log equivalent of saying something like 10 to the A plus, sorry, times 10 to the B is equal to 10 to the A plus B. This is just our additive law of exponents. This is the log property that goes along with it. Now, similarly, just like we have an additive law of exponents, we also deal with negative exponents. And if I have log of A divided by B, that's the same as log of A minus log B. And there's one more log rule that maybe we use even more than either of these two. And the last one looks like this. Well, let's say that I had log of x cubed. Well, I can think of that x cubed as really being log of x times x times x. And then we can exploit that first log rule to break that apart as addition and say log of x plus log of x plus log of x. And our shortcut way of writing that would be 3 log x. So as a general rule, if I have log of x to the n, this is equivalent to n times log x. And this one right here, this last one, we use this a lot in calculus because it's sort of how, it's one of the tools that we have to pull exponents out of the exponent and be able to work with them. Okay, these are like our 3 log rules that were, oh, question? Yeah.
For the third one, is it like a special step for us to get the end to the front, or is it just automatically goes to the front?
So if this is like a single number raised to, like if this is something raised to a power, it is equivalent to this. You could write out these 3 steps, but you don't have to. You're not expected to. I happen to think it's kind of a waste of time unless you need to do it a few times to kind of solidify what the rule is in your head. Absolutely, we should go straight from here to here. Now, all of these things work no matter what the base on the log is. So we can write all 3 of these rules in terms of their natural log components also, right? So this was all with an LOG, so the base implied is 10. But the rules are exactly the same if we switched it to natural log. So if I switched it to natural log, these rules would look like natural log of A times B is equal to natural log of A plus natural log of B. Natural log of A divided by B is equal to natural log of A minus natural log of B. And natural log of x to the n is equal to n natural log of x. Now I checked before class and I did not see a homework 3 posted. Okay, so I'm not sure what kinds of questions he's going to ask you in terms of just log stuff, but it's a calculus class. I know we're going to have to do derivatives. So I definitely want to dive into talking about derivatives of logs and mess around with properties of those derivatives of logs. Questions about this before we like do some stuff? Okay. Okay, so thinking about derivatives of logs, I realized I should have mentioned one other thing first, and that is that we've got this. Here's the one I always fall back to, but log base 2 of 8 is equal to 3 because 2 to the third is equal to 8. Well, logs and exponentials are inverse functions of each other. And the inverse of the inverse function for e to the x is natural log of x. Now, the reason that that's working out here, if I said y is equal to e to the x, sorry, I should have put that over here. Y is equal to e to the x, then our, that, then our log equivalent statement of this would say, okay, well, my base is e, so that would be log with a base of e. What's in the place of the 3 there is the x, that's the exponent part. And then the 8 is what went inside over here. But this, our shortcut notation for writing log with a base of e is to say natural log. So these are really our equivalent statements. And what that means is that if I take the natural log of e to the x, and I wasn't sure what that was equal to, well, if I rewrite that as an exponent statement, then the base, the invisible base here is e. So this would say e to the question mark is equal to e to the x. So I've got that invisible e down here, raised to the question mark is equal to e to the x. And that must mean that that question mark was equal to x, or that the natural log of e to the x is equal to x. Now I know this might feel like a whole bunch of rules. Hopefully it's just refreshing your memory about stuff you've seen in a previous life. If it really feels brand new, you can let me know, but I'm going at a pace kind of assuming that we're just bringing back some memories from the distant past. Yeah, good times. So now we can fast forward to talking about derivatives a little bit. And I'm going to start by saying, okay, well, what if I had y equals e to the x, and I want to take the derivative? You all know what the derivative is. This says y prime is equal to derivative of e to the x is? Okay. I'm going to keep that off to the side for us, just so that we remember things. But actually, our function is going to be, I need another letter, y, how about z, sure. Z is equal to the natural log of x. And what I want to do is take the derivative. But I don't know what the derivative of the natural log of x, well, I do know what the derivative of the natural log of x is, but we're going to pretend for a second that I don't know what the derivative of the natural log of x is. And instead, I'm going to rewrite this in its exponential form. So in its exponential form, there's that invisible e. And this says e raised to the z is equal to x. E to the z is equal to x. Now this next part is going to be a big ask, because I'm asking you to pull something from your 16A knowledge. And I don't know when you took 16A, but chances are good your class was on Zoom. So I don't know how that went down, but we're going to use implicit differentiation to take the derivative of both sides. So let's do the easy side first. What is the derivative of x? Not a trick question. What is the derivative of x? Yes, thank you. Okay. And we know that when we take the derivative of an exponential, we get e to the stuff times the derivative of the stuff. I'm just going to write that as z prime. Well, what we were trying to do was find z prime. Our objective was to take the derivative of z. So if I divide both sides by e to the z, then what we have is z prime is equal to 1 over e to the z, or 1 over x. So our thrilling conclusion here is if y is equal to e to the x, then y prime is e to the x. If y is equal to natural log of x, then that derivative is 1 over x. And these really are our two derivative rules for chapter 4. Everything else we're doing with those derivatives is building off of these two fundamental rules. So this is the part that you want to make sure you have memorized. Derivative of e to the x is e to the x. The derivative of natural log of x is 1 over x. Yeah.
Is the like, 1 over e to the z also equivalent to e z to the -1?
Absolutely. You could call that easy to the -1. The reason that I'm writing it this way is because e to the z was equal to x. So I kept it in this form to get us back to really what I'm aiming for, which is that derivative rule for natural log. Just like we can apply product rule and chain rule and quotient rule and all those fun things to taking derivatives of exponentials, we can do all of those things with derivatives of logs as well. Usually, almost always, we're dealing with natural log in calculus because it's easier. We can do this same process to deal with a log base 10, but it's slightly messy, and I'm going to wait till Friday to deal with that. For today, I want to stick with our easiest option, which is natural log, and get some more examples. So let's just practice taking some derivatives. If my f of x, let's say I have natural log of 3x minus x squared. I don't know why I made the first one so messy, but I did. Well, first of all, when we have a problem and it's got natural logs in it, one of the first things that I might look for is to see whether any of our log rules can simplify parts of the problem. Unfortunately, here, the answer to that question is no. If I had multiplication or division inside of the log, that we can break apart. I can't break apart addition or subtraction. So we're stuck. There isn't a log rule that's going to help us. We just have to go straight into the derivative. Now our rule for the derivative is we're going to get the derivative of natural log of something is 1 over the something. So this is going to look like 1 over all that stuff, 3x minus x squared times chain rule. Chain rule is going to follow us wherever we go. So when we take the derivative of the inside using chain rule, I'm going to have 3 minus 2x. Sometimes what I see get written is if y is equal to natural log of some function of x, then y prime is 1 over that function of x times f prime of x, or that gets written as like f prime of x over f of x. I just think all of that is extra clunky notation. But it can be helpful to remember what's going on with the chain rule. Just as a like reminder, we should always be thinking chain rule. I keep checking the chat, but no one on Zoom is asking me questions in the chat. Just so you know, I really do have it open. I really am looking at it. Slow me down or speed me up if you need to. What question?
No,
You sure?
that was because I tried my back, it was really loud.
Oh. Was it satisfying? Did it feel good? Okay. So let's say I've got x squared natural log of x. Do you want to practice product rule on your own? Okay, I'll give you a minute to try it on your own. So as a product rule here, I can separate this as two pieces. I've got the x squared times natural log of x. So when I come in with a product rule, derivative of x squared is 2x times, we'll leave the natural log of x alone, plus we'll leave the x squared alone and multiplied by the derivative of natural log of x. Derivative of natural log of x is 1 over x, yeah. So we can, now there are options for how we can deal with this now. We can probably just leave it alone, but if I didn't want to, if I wanted to clean this up just a little bit, I could take that x squared times 1 over x and just write that as x. I am not being mean, asking you to take the derivative of this thing. But it would be in our best interest to take a look at this kind of messy thing, natural log of x cubed divided by the square root of x minus 1, and pause for a second before we start taking the derivative. We've got a bunch of stuff jumbled up inside of that natural log. And before I skip into a derivative, I want to go ahead and rewrite this using log rules. So the biggest thing that I've got here is division, and I know that I can break that apart by saying natural log of x cubed minus natural log of the square root of x minus 1. And then my next log rule that I'm going to apply is the one with exponents. And that log rule with exponents, it's going to come up a lot. It's one that we definitely want to have at our disposal. So this I can jump into rewriting as 3 natural log of x. With that square root, the exponent on the x minus 1 is a 1/2 because we had that square root. So I can rewrite this side as 1/2 natural log of x minus 1. And that's looking way better to take a derivative of. Now I'm ready to come in with the derivative. You could do a product rule here. We don't need to do a product rule because it's just a number. So that like second part of the product rule, that derivative of 3, or I guess the first part, whatever, but the derivative of 3 would be equal to 0. So we wouldn't even have that part. So this is just going to look like 3 times 1 over x minus 1/2 times, we've got natural log of something, so it's going to be 1 over the something. For completeness, I would apply the chain rule, but the derivative of x minus 1 is 1. If you wanted to rewrite that, we could. We certainly could look at that 3 times 1 over x, write that as 3 over x. Not much we can do with this. So I would probably leave it right there.
Professor?
Yeah.
Just to be clear, the times one at the very end was from the S.
The times 1 at the end is from taking the derivative of x minus 1. So the derivative of that x would be 1 and the derivative of 1 would be 0. So I didn't write the minus 0 part. Yeah. Now, if we use homework 2 as a guide, you might have to do some graphing with log functions, right? Because homework 2 had some graphing, or no, homework 1 had some graphing of exponential functions. So should we graph some log functions? As a guess that might show up. Okay, so if we take a look at sketching log graphs, when we were drawing exponential functions, and I will just go ahead and get in here our y equals e to the x graph. Our exponential functions are characterized by a y-intercept and a horizontal asymptote. Well, I mentioned that y equals e to the x and y equals natural log of x. They're inverse functions. And I don't know if you remember from a previous life, but when you're graphing inverse functions, you're reflecting them over the y equals x line. So our graph for log functions are characterized by a vertical asymptote and an x-intercept. So just to review a few quick sort of facts about our logs and exponential functions. And I feel like we did this that very first Friday, some of this while we were over in Dutton Hall and I was dealing with the chalkboard, but e raised to the 0 power is equal to 1. E to the first power is approximately 2.718. We could keep going, but that's plenty. We looked at the limit as x approaches infinity of e to the x, and that was positive infinity. And if we take the limit as x approaches infinity of e to a negative infinity of e to the x, that goes to 0. So I kind of want to look at what those similar facts are for our log function. So that first statement, the e to the 0 is equal to 1. Well, natural log of 1 is equal to 0. Because these two are equivalent statements. This one we could put in its exponential form by taking that invisible exponent of e and saying e raised to the 0 is equal to 1. So these two are equivalent statements. Natural log of E is equal to 1. And that's because if we write this as an exponential statement, this is saying E raised to the first power is E. Now, the interesting limits on this log graph, so if I take the limit as x approaches positive infinity for our natural log graph, that also goes to infinity. This is going up and up and up and up. Now, our natural log graph, we can only take the natural log of a positive number. Now, the reason that that's happening is if we think about that relationship between our log and our exponential statement, right? I don't know which one I want to go with. Let me just, if I think about y equals e to the x versus if I rearrange this to say natural log of y is equal to x. For that e to the x function, no matter what we put up there for the exponent, the answer is always a positive number. E is about 2.7. No matter how many times I multiply that by itself, the result is always a positive number. Well, that means that this is always going to be positive, or by contrast, what we put into the natural log always has to be a positive number. So it doesn't make sense to take a limit as x approaches negative infinity. That's not on our graph. The limit of interest for the natural log is to look at the limit as x approaches 0 of natural log of x. And here our answer is negative infinity. So as we get closer to 0 on the axis here, our y values are headed down to negative infinity. So that's sort of our equivalent limit of interest for logs. Pausing for questions. Yeah.
So it doesn't go negative because of the vertical asymptote. It's not like any chance or problems that were the vertical asymptote was negative.
Yeah, we can totally shift where that is. So let's say that I wanted to sketch. There's a C in the word sketch. So let's say that I wanted to sketch y equals 2 ln of x minus 3. Well, from like a domain perspective, whatever is inside of the natural log, that part has to be greater than 0. So this would tell me from a domain perspective that x minus 3 has to be greater than 0, or x has to be greater than 3. And that just pushed my vertical asymptote over here to x equals 3. Whenever we're graphing whenever we're graphing exponential functions, we always have a y-intercept and a horizontal asymptote. Well, when we graph logs, we always have an x-intercept and a vertical asymptote. Our vertical asymptote really we get from the domain by thinking about what makes that, whatever's inside of the log, what makes that equal to 0. And x-intercepts we always get the same way by setting y equal to 0. If I do that here, I've got 0 is equal to 2 times natural log of x minus 3. I can divide both sides by 2, but 0 divided by 2 is still 0. If I want to solve this, the way I'm going to solve it is by rewriting it in its exponential form. So there's that invisible base of e raised to the 0 power is equal to x minus 3. So e to the 0 is equal to x minus 3, or 1 is equal to x minus 3. X is equal to 4. So this would have an x-intercept of 4. And then we would just sketch in the shape of the log. I don't want to leave without showing you this trick, just because I think it's cool. I hadn't seen it before. Grant showed me. I don't know if any of you know Grant. He's one of my colleagues. If you are lucky, the natural log is so natural, it's on the palm of your right hand. If you're lucky, you've got e to the x, the y equals x line, and natural log of x. That's all we have time for today. Oh, the hand? Yeah. So if you're lucky, like if you kind of like crunch your hand up just a little bit, you might have this top crease that kind of follows an exponential shape, and then a y equals x line because it's reflected across because they're inverses, and then an ln of x curve at the bottom. Only works on your right hand. If you use your left hand, you get the negatives of all the graphs. That's no good. Don't get that wrong.